Assalamu alaikum. Welcome to the fifth lecture on advanced computer architecture. In our previous lecture, we discussed the instruction set architecture of a simple processor called SRC. We looked at different classification of the instruction sets, and then we also considered some examples of different types of instructions like add, which is a basically arithmetic instruction. We also discussed the logical instructions like AND, OR, then shift operations. The second class of instructions where the interaction with memory is involved, we discussed the load and store instructions, and then we discussed some examples of hand assembly. In the case of hand assembly, when the mnemonics in assembly language are given by hand, we try to write the corresponding machine language equivalent. Nevertheless, this is not so simple and tedious. The programs like assemblers are available to automatically convert the assembly code into machine code, and such an assembler is available in your coursework, and you could practice with hand as well as by using this assembler. Today we'll continue to discuss the reverse operation of a reverse assembly, or also called disassembly. Then we'll continue the description of this SRC in the form of RTL. We'll define RTL and discuss the behavioral and the structural description in terms of RTL. Let us first look at the slide to illustrate the concept of reverse assembly. Reverse assembly is just the opposite of assembly. Typical problem is as follows. We are given a machine language instruction for the given processor, which in this case is SRC, the simple RISC computer. It may be required to find the equivalent SRC assembly language instruction. The typical example is given in the slide. Instructions in the form of machine language are given. The solution proceeds as follows. First of all, the given hexadecimal instruction is converted into its equivalent binary form. In this example, the hex instruction corresponds to 68C2003A in hexadecimal. Each hexadecimal is converted to 4 bits of binary form. As a result, we have 32 bits. Examine out of these 32 bits the first 5 bits, and these 5 bits would correspond to mnemonic for the SRC instruction. That means it would be the opcode for this particular instruction. We need to consult the table which is available to you for SRC. So in this case, first 5 bits are 0, 1, 1, 0, 1. In terms of decimal, it is 13 decimal. Looking in the table for SRC, it corresponds to add immediate instruction. After looking at this opcode of add immediate, we now have to analyze rest of the bits. The rest of the fields would correspond, in this case, the next 5 bits from 6 to 10 would be representing the placeholder for register RA, which is in this case 00011, and it corresponds to decimal 3. So therefore, it would be representing the register R3. The next 5 bits correspond to the field RB. The RB field in this example is 00001, which is decimal 1, and therefore for RB it corresponds to R1. Remaining 17 bits represent the constant. As you know, it's a type C format for SRC instruction. Looking at this constant and converting the hexadecimal into decimal, 3A hex is equivalent to 58 decimal. Therefore, the corresponding assembly language instruction would be add immediate R3, R1, 58. As a summary, for the total program, the first row corresponding to the machine language 68C2003A hex has been interpreted by using the hand reverse assembly as add I R3, R1, 58. This just illustrates the procedure for hand reverse assembly. Remaining instructions could be just analyzed exactly in the same way. So quickly, we have illustrated in the next slide the equivalent instruction in binary for each row. So we need not go into the exact details, and you could just see the next column analyzing the first 5 bits which represent opcode. This field is interpreted in the form of assembly, and it corresponds to shift left, add, subtract, store, and load. Now this procedure could be followed either through hand, or you could use the tools as a disassembler to arrive at the assembly language. We'll see in our later slides the assembly and disassembly being done by one of the programs, which is a simulator written by our team. The instruction sets describe the operations. When an assembly program would run on a particular processor, the processor would interact with the memory and all of its resources in the form of different registers. We need to describe the operation of SRC, both in a static form as well as in a dynamic form. We need to have some tool for that, and that is RTL. RTL stands for Register Transfer Language. In your book, this terminology is slightly different. It is given as RTN, which is Register Transfer Notation. We'll prefer to use the notation as language and call it as RTL. It is a formal way of describing the operation of SRC. So we'll look into some details how RTL would describe the operation. There are 2 aspects which RTL description would cover. The first one is the behavior, and we call it behavioral description, or the behavioral RTL. In the book, it is designated as abstract RTN. Let us use just the behavioral RTL. The concept in this case is that what the processor would do. The emphasis is on what? We just consider as a black box and see the operation as a black box. So the second aspect would be the structural behavior, and then we'll call it structural RTL. And we'll explain these concepts with the help of some slides. The behavioral RTL would just explain the operation as a system. We'll consider the total processor as one system, subdivide it into some subsystems, and each subsystem would be further divided into further subsystems till we come to some basic elements, and this would be an analysis process. The converse would be the synthesis process or design process. After understanding the basic elements of the total system as smaller subsystems, then we'll link them together, put them together, and just come up with a design. And this description would be called behavioral description in the form of RTL. And the example would be our processor SRC. The second aspect is the structural RTL. In the case of structural RTL, we are concerned with implementation. This would deal more with the details of how those things would be done, how the instructions would actually be implemented, and that would bring us to some more hardware features. We'll look into these in later slides. Let us now see at the slides to illustrate the concept of the behavioral RTL. As we said, RTL would be a tool to describe the static and dynamic properties of SRC. Let us see first how do we specify registers using RTL. The first example says IR with an angle bracket 31.0 angle bracket closed, which means that bit numbered 31 to 0 of a 32-bit register which is named IR, that is the instruction register. So using the RTL notation, IR 31 to 0 with this notation would specify the IR register. Same way we could specify other registers like the PC, program counter, and general purpose registers from R0 up to R31, because there are total 32 general purpose registers. Secondly, the naming concept or putting an equivalence is given with the help of another example. OP, which stands actually for the opcode, again with the angle brackets 4.0 and then a colon followed by an equality sign, and on the right hand side we have IR within angle brackets 31 up to 27. This means that the 5 most significant bits of the instruction register IR would be called as op within brackets 4 to 0. That means 5 bits of the op code. Now please note that this process does not create a new register. it just generates an other name or alias for an already existing register or a part of the register. So why we need to define different bits in the instruction register? They correspond to different interpretations. Let us look at the next slide. In this case, using the equivalence operation, first 5 bits are named as OP, designating opcode, and using again the RTL naming operator, that is colon followed by an equality sign, and that would be taken out of the IR register using the most significant bit, that is the operation code field. The next 5 bits, represented by RA within angle brackets 4 to 0, are equivalent to IR bits 26 to 22. Note that on each side, right hand and left hand side, the number of bits must be equal. It should be consistent. And that represents the target register field. That means RA, as we discussed earlier, is a placeholder and would usually represent the destination register. Next 5 bits in IR are named with an alias RB within angle brackets 4 to 0, and that would indicate one of the operands, the address index or the branch target register, depending upon the opcode or the type of instruction in question. Similarly, RC is a placeholder and the information would be taken from bit number 12 to 16. The next 3 constants C1, C2 and C3 are represented. You will appreciate from the structure of the instructions that all C1, C2, C3 would not simultaneously be present in one instruction, and either one C1 or C2 or C3, depending upon which type or which class of instruction we are discussing. Similarly, we can describe the state of the processor by contents of different registers. For example, PC, again with the angle bracket 31 up to 0, represents the program counter, which would indicate the next address corresponding to the memory, and it would point to the next instruction or data to be fetched. IR we have already discussed. There are 2 other 1-bit registers. One is a run, and it is just 1 bit. Either the processor is in run mode or it is in halt mode. And we have a start, again a 1-bit indication for start signal, and 32 general purpose registers. Using the RTL notation, we just indicate the status of a processor by the contents of different registers. We could imagine static description of the processor in the form of a black box, which is given in the slide. The run could be taken as a simple indicator, and similarly start could be interpreted as a switch on the front of the black box. There could be many other connectors at the back of this black box, which we will not discuss at this moment, and we can add later as and when required. It is important at this stage to point out that there are some differences in the notations used in the book, your textbook, and the material which we are going to cover in these lectures. I'll just point out a few. Others would be clear as we go through the RTL description. As we said that in the book, the terminology used is RTN, whereas we are calling it as RTL. Instead of notation, we call it a language. Now please note that for testing a condition, we will be using the notation as colon, whereas it is indicated by a right arrow in your book. We would not like to use the right arrow and prefer to use the colon. This might be one of the standard notations used in other books. Similarly, we have a concept of concurrent statements. There would be some concurrent statements used. We will use a colon for representing the concurrence, whereas in the book it is a colon which is used. Similarly, the other symbols are different for logical operations like and or, and our symbols would take the precedence, and the handout is given in your course material for the symbols which would be used for these presentations. The contents of the registers which we have described using the RTL notation give us the static properties. However, when we run a program on the processor, the contents of different registers would change, and we need to have the dynamic description, that is, the dynamic properties of the SRC are to be defined. And let us take some examples how to define these. In the given slide, we see a conditional expression. For example, on the left-hand side, we have opcode equal to 14 in this example. And then we have a colon which just represents a condition. And on the right-hand side, we have an expression. Now please note that it is a construct like if, then in higher language. So the left-hand expression, which would be a Boolean expression, would be evaluated. If it is true, then and only then the right-hand expression would be implemented. In this example, we see that the right-hand expression is R within the square brackets small r a, and then we have the RTL assignment operator given by left arrow and RB minus RC. This says that if the off field is equal to 14, then calculate the difference of the value given in the register specified by the RB field and the value in the register specified by the RC field, and store this difference in the register specified by the RA field. At the end, we have a semicolon, which is a sign of termination in RTL notation. That means after the semicolon, the next operation would start, anything else can start. So once again, this is an example of a conditional expression written in the form of RTL notation. We can consider some other examples using RTL notation. Evaluation of address is important, and in the next slide, we have an example where the displacement address and the relative address examples are encountered. Please note that evaluation of these addresses is done at the run time and not during the assembly. In the expression, the left-hand side defines an alias DISP, which stands for displacement address, again with the angle brackets 31 to 0 indicates that this would have 32 bits, and then we have an assignment operator, and on the right hand side, first condition is RB equal to 0, then a colon which would indicate the condition, meaning that in case the contents of the placeholder RB are 0, then do what? On the right hand side, the constant C2 within brackets 16 to 0 means that this constant has a 17-bit field, and then again within brackets sign extend means that bring it to 32 bits by copying the more significant bits with the sign bit. So therefore, if the placeholder is 0, RB is 0, then extend and execute or assign the 17 bits and put it as a displacement address as 32-bit address. The second option is that if RB is not 0, and please note there is a comma which we explained that it is representing concurrence. That means the two conditions would be concurrent and take place simultaneously. In this case, both cannot occur together. These two are disjoint conditions. So if RB is not 0, then do what? The condition is the contents of the register represented by the placeholder RB, that means R within square brackets small rb plus the constant C2 sign extended, and then again the bracket closes. So this is an example of representing the calculation of displacement address written in RTL notation. At the end, we have again a comma, and this would just depend on the context. We could have a semicolon. If we had a semicolon, that would mean that this particular condition would just finish and something else would start. And a colon would mean we could have another condition or another statement which could be simultaneous or concurrent with the previous conditions. The next example shows the relative address, that is the PC relative address, and on the left hand side of the assignment operator we have REL standing for the relative address. Again it is 32-bit indicated with angle brackets, and within angle brackets from bit 31 up to 0. That is, it is a 32-bit data. On the right hand side we have the contents of PC represented by PC within angle brackets 31 to 0 plus the constant C1 from bit 21 to 0, and again you see that C1 is a 22-bit constant and it has to be sign extended in order that we can add it to the contents of the PC. So this relative address would be calculated by adding the contents of the constant C1 to the contents of PC, and that could be, for example, used in a shift instruction. In the last slide, we have seen how to represent the displacement and relative addresses using RTL notation. It's important to note here that what would be the addressability range in these two cases. For the case of displacement address, when the placeholder RB is 0, that means the contents of the second register are 0, this would be equivalent to having a direct address because offset would be 0 in this case. What would be the maximum range of the memory which this address would indicate? Let us say when the placeholder small rb is equal to 0 and the address is a direct addressing mode. There are two possibilities. Either this constant C2 could be positive or negative. If it is positive, then its most significant bit, that means within angle brackets C16 would be 0, and that would mean that the memory which is represented by direct address would be from all 0, 0, 0, 0 up to F, 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 and that indicates the positive range of addresses at the bottom of the memory. On the other hand, if this constant C2 is 1, indicating a negative value of this constant, then in that case our range of addresses would be at the top of the memory starting from F, 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 then 0, 0, 0, 0, 0 to all F's at the top. On the other hand, if we have the second PC relative address, then the constant which we have is C1 and it is a 22-bit constant. Again, this could be just positive or negative. The maximum positive value for this would be 2 raised to power 21 minus 1, and the maximum negative value would be minus 2 raised to the power 21. The next important representation to be dealt with in RTL is the concept of fetch and execute. As explained in one of the earlier lectures, the processor would fetch an instruction, decode, and execute, and this cycle would continue. And let us now explain the concept of fetching the instruction, executing, and then repeating this cycle in the form of RTL notation, and that is shown in one of the following slides. This slide indicates the instruction fetch. On the left hand side, the instruction fetch with an assignment indicates the concept of instruction fetch. Now, instruction could only be fetched if the processor is previously not running and therefore indicated by not run, and somebody pushes a start button or would like to start the operation. So therefore, the first condition is that not run and start, and this would give us the contents of the run register, which is a 1-bit register, as 1. So the second line indicates that the previous condition for the processor was not run, it was not running, and then the start instruction comes, which is again just indicated by 1 bit, and we will have run assigned as 1. Now a comma indicates that after this, the concurrent statement is, if run has been 1, now what is to be done? The contents of the memory location indicated by the present contents of PC, the program counter, are brought to the IR instruction register. And again, the second comma indicates that these two statements are simultaneous or concurrent. So this would mean that contents of the PC, the program counter, are updated by 4. So 4 is added to the program contents, and that is to be placed in the program counter, which would be indicating the next position in the memory from where the next instruction would be fetched. Then we have a semicolon followed by instruction execution, and then the bracket closes and we have a semicolon. This is a very important representation of the instruction fetch and instruction execute. Now, the indicators are very clearly given, and please see that the two instructions I are assigned with a value M of PC and PC updated by 4 are concurrent, and that is indicated by a comma. And that would mean when two statements are concurrent, you could swap these two and the order would not matter. Although physically these two statements might be processed one after the other, but in terms of RTL notation, we say that these two statements would be concurrent. As an example, when the contents of program counter PC are 8, and then there is a confusion that the next contents would be 12. So the instruction register would take up the contents from memory location 8 or from 12. The rule is very simple, that the left-hand side would not be updated till both the concurrent statements or all the concurrent statements are executed or evaluated. So in this case, there should be no confusion that first IR register gets the contents of memory location indicated by program counter, and then program counter is prepared for fetching the next instruction. So this is a representation of the fetch and execute cycle. Once the instruction has been fetched, it needs to be decoded and executed. We need to understand the execution process. In RTL notation, the decoding and the execution is just indicated by one process, and it could be represented in the form of a number of conditional instructions or a representation given by a number of conditions. Let us see how do we represent these conditions in the form of RTL notation, and that is shown in the next slide. This slide illustrates the RTL notation for the execution of the fetched instruction. As already explained, that execution and decoding would be done together, and this is represented by a list of conditional operations which are inherently disjoint. In this relation, on the left-hand side, IE stands for instruction execution. Then we have assignment operator, and on the right-hand side, the first condition is indicated by opcode equal to 1. which corresponds to the assembly instruction load. And what is to be done? So it follows that if opcode is 1, then do what? Take the address calculated by DISP, which is a displacement address, fetch the memory contents from this address and place into the register coded by the placeholder RA. Following this operation, we have a comma, which means the next operation is concurrent. So the next one indicates opcode equal to 2, which is load relative. And in this case, what we do, we take the relative address calculated by updating the contents of PC and put it into the register indicated by the placeholder RA. This sequence continues till, for example, the last one with an opcode of 31 indicates that now the whole sequence is finished, and put a 0 in the run. And this would prepare the processor for the next instruction. Now we have a semicolon indicating that all this sequence of disjoint conditional operations is done, and then IF is fetch the next instruction. So this cycle would continue: instruction fetch, then execute, again fetch, and execute. At the end of this list, as I've already explained, the semicolon is an indication of the next operation. And the next operation in this case is IF, that would be invoked after every loop. In the next few slides, we will look at this long list in somewhat more detail. A flow diagram is indicated in the next slide. The top block indicates the instruction fetch. Then we have instruction decode, which practically would mean looking at the first 5 bits of the fetched instruction, which would indicate the opcode. So this opcode may be 0 up to 31, depending upon the contents of this opcode, the value of this opcode. An appropriate processing would take place. After the processing has taken place, then we will go back as a loop and the next instruction would be fetched. This is exactly the symbolic representation of the previous RTL notation for the fetch and execute cycle. By now, you might have noticed that hand assembly and reverse assembly is not an easy job. It's quite tedious and prone to errors. So in practice, you will be working with an assembler, and to get an in-depth concept, we have also provided you with a simulator. This simulator would give you the status of different registers and the memory, and it would also provide you with the opportunity of having a single step operation. That means executing one instruction at a time, and then you can also watch and see the contents of different registers, program counter, instruction register, and at will you could also change the contents of any memory location or register arbitrarily. For going through these concepts, let us see at a few following slides for detailed concepts. The first slide shows a very simple program written in assembly. We want to assemble this by using our assembler. Our assembler is DOS based. You need to go to command prompt, which is just indicated in the next slide. The files available to us, the programs, are the assembler, the simulator, and a test file which we have already seen that is named as tst.asm, and we need to assemble this file using the src assembler. So we just say src asm tst.asm as indicated in the next slide. After the assembly, we see that there is an error, and it has reported in the first pass an error. Let us see what was the error. It shows that there is an error at line 1, invalid instruction org. It should have been .org, which is corrected in the next slide. And we reassemble it, and now we see that in the two passes it has just generated the two files, a list file and a binary file. Now the files are available with us: original source file, which is in assembly, a list file, and a binary file. The next slide shows the results after running the assembler. You just see that the memory locations are given both in hex as well as in decimal, and the corresponding the machine code is indicated in the third column. The assembly program originally line by line is also indicated. The final test file in binary form is given in the next slide. Next slide shows the basic simulator. You see there are 4 windows. The first top left window indicates the contents of the registers. There would be 32 registers. Next lower window indicates the result in the form of address. The next 2 windows give the contents of the memories at 2 segments which could be selected. Let us load the binary file generated by the assembler into this simulator. After loading, you just see the corresponding contents. In the beginning, all the 32 registers have contents as 0, and the memory segment starting from address 3F0 onwards is indicated. We could execute the program in single step. So in single step mode, one could view all the details, the contents of different memory locations as well as the registers, as illustrated in the few slides. One could execute the program without having any breakpoints, and if we execute the program without break, then it would go in one run and the final contents would be available for all the registers. You would realize that the assembler and the simulator are very friendly tools. Using the SCR instruction set architecture, I would recommend that please go through a number of exercises till you could easily talk to the assembler and the simulator. the simulator in particular would be quite useful to give you an insight into the operation of the processor. In particular, concentrate on the RTL notation which we have today introduced and see that this RTL notation given in the simulator is according to what we have discussed in the lectures and not what is given in the book. Take a note of these differences so that you do not get confused. RTL is a formal way of representing both the static as well as the dynamic operation of this sample processor SRC, which we have been discussing. The idea of discussing this processor as an example is to give you an insight into the architectural features of the processor. As you have realized by now that ISA, the instruction set architecture of the processor, is extremely important, and a designer or an architect of the processor would first of all design this instruction set. But before we can go to the design process, actually we need to understand what others have designed, and therefore this was an example processor to give you the basic concepts. After mastering these basic concepts, you could just go into more complicated implementations and see other processors as well. Just to give you a review of what we have done today, we just introduced the RTL notation. This particular concept of formally describing the operation of a particular processor is important. So instead of just banking on the assembly program, we would make it more useful by observing the RTL notation as well. The RTL notation gives both the static aspects, whereby we just know what are the contents of different registers. On the other hand, the dynamic RTL representation gives us the opportunity to observe the changes in the contents of different registers, and therefore during execution we could just debug and see the operation of the program. Finally, the key concept which we have talked about is the fetch and execute. We have given an RTL formal representation and the notation for the fetch and execute cycle. We have seen that the execute cycle could be represented in the form of a multiple conditional operations, and each operation would be executed depending upon the opcode given in that particular part of the instruction. The fetch and execute concept continues one after the other till we have completed the execution of our complete program. I would suggest that you please go through the concepts of RTL representation in detail, and you could compare the notations used in the book with that what we have followed. Nevertheless, try to follow all the notations which we have used in the presentation, and do not get confused with the notations given in the book. Next time we'll continue with the RTL notation after completing the behavioral concepts, we will continue with the structural concepts of RTL. Till next time, Allah Hafiz.